The eye coverage for those, so these are the ones we test regularly. So these are the supported ones. Visual C++ and GCC are supported, and a few different variations of GCC. So on SIGWin on Windows and MinGW. There's some initial support for publishing your binaries to a binary repository manager, and some even more initial support for resolving. That stuff isn't quite there, so you can publish but you can't resolve them. So there's an obvious roadmap item there. And there's some integration with Eclipse. So like we do with the Eclipse JDT, we can generate the settings, the project files and settings for the Eclipse CDT as well in the same sort of way. So some caveats before we get started. The current support is incubating, so that means it's a work in progress. Some things are missing, some things probably don't work as well as they could, and we're probably almost certainly going to change things in breaking ways as we get further down our roadmap. But it does some good stuff, as you'll see already, and we've just gotten started on a chunk of work for over the next 3 or 4 months, and we want to add quite a lot of good stuff there. So expect to see some nice new features over the next 2 or 3 releases. So I'm going to show you the stuff that's from, so I've already started some of that work, and so I'm going to demo that today. So this stuff that I'm showing you today will be in the 1.7 release in a couple of weeks, a couple of weeks, whenever that happens to be. Yeah, all right. So don't try doing this stuff with 1.6 because it's not going to work. So let's start with building an executable. So we have the CPP exe plugin, and that's a build by convention plugin. So if I put my source in the right places, source main CPP, and my headers under source main headers, Gradle will find that, it'll compile all that stuff, link it into an executable. It'll do that using whichever toolchain you can find in the path. So if it finds GCC, it'll use GCC. If it finds Visual C++, it will use Visual C++. And that's all wired into the standard lifecycle, so you can basically do Gradle, assemble, and you'll get your executable. So very similar to the Java plugin, build by convention stuff, wired into the standard lifecycle, put your source in the right place, it'll just work. So there's some basic customization you can do with this guy. You can tweak the compiler settings and the linker settings, and you can customize the source directory layout, because you're probably almost certainly not using this convention for your C++ projects at the moment. So even if there is a convention in the C++ world, who knows? So you can tweak where things are, but you get all the lifecycle stuff. So let's take a look at this in action. So I've got my hello world executable here. So I've got my source down here, source main CPP. I've split it up into a couple of C++ source files, because that's what you've got to do with a hello world app. It's got to modularize a bit. And I've got my headers here. So the conventional locations where the plugin's expecting that. And if we have a look at our build script, pretty simple. So I'm just saying, Gradle, go and look in the places, the conventional locations, and build me an executable. So let's do that. So, what's it done? So the first thing it's done there is set up incoming header files. So this is used when you're declaring dependencies on external libraries, and this will take care of getting those the header files down out of the repository, installed in the right locations, and so we can hand them off to the compiler. Our Hello World doesn't have any library dependencies, so that didn't do anything. Then it takes our source files, compiles them into object files, and then takes those object files and links them into an executable. Got our assemble lifecycle task. So let's see what it's done. So it's built our Hello World executable, and then we've got our some temporary files. So it's built some object files for us and some other temporary stuff. So we can run our Hello World app, and it should all be good. So let's run that again. So we'll build that again. So everything's up to date. So the C++ tasks are all wired into the incremental build features of Gradle. So I didn't change anything, so everything's up to date. My executable's still up to date. So let's change the source file here. And we'll add an optional feature here. So if the farewell preprocessor macro is defined, we'll say goodbye as well. So let's run that again. We haven't defined that macro. All we've done is change the source. So Gradle's noticed that the source has changed. It's recompiled the source files into object files. But because I haven't defined that macro, the object files haven't changed. So I don't need to do any linking. The executable's already up to date. So because we're using hashes for the up-to-date checks, we can short circuit the build as soon as there's no further changes. So if you compare that to something like a timestamp based build system, because the object files, their timestamps would have changed, it would have relinked the executable, even though it didn't need to. So we've got some smartness in the incremental build there that understands the content. So let's go and define our macro now. So we'll tell Gradle, when I'm building the executable, I want to define that preprocessor macro. So we're going to say, well, the main executable, which is something that this CPP XE plugin defines, and for every binary that I build for that, I want to define this preprocessor macro. So for the main executable, for all the binaries that you build for that executable, define our preprocessor macro. So let's build it again. Well, that's good. Missing a column there. Let's do that again. So Gradle's noticed that this time the settings have changed and the source have changed. Recompiled it. So the resulting object files are now different because the macro was defined. So it's going to generate that extra code. It's going to relink the executable. So if we run that, we get our nice friendly goodbye as well. So let's change a header file now. So I'm just going to make a change that doesn't affect the output here. So I'll just put some divides in there. So again, it's noticed that a header file's changed, it needs to recompile the source, but that didn't affect the object files, so no need to link. So the incremental build understands changes to the source files, to the header files, to the compiler settings, also to the linker settings. So let's look at our build file again. So what we've got here is a high-level description of what to build. There's nothing here about how to build it. We didn't tell Gradle here about how to run GCC, how to link executables. We've got a high-level definition of what it is we're building rather than how to build it. We can do some settings there. We can dive down if we want to and actually drive the compiler if we want to. And for most projects, that's probably the reality, is that you're going to need to start adding. Let's make an optimized hello world. So we can tweak the compiler args and the linker args and so on when we're building our binary. So, nice high-level description. We get some tasks for free, so Gradle knows how to compile that stuff, link that stuff, and build an executable out of it. So building a library is very similar, but a little bit more interesting. So we have the cpplib plugin is another build by convention plugin. Same sort of conventions. What's different about this guy is that you can build from the same source. You can build either a shared library or a static library, or both, depending on what you need. So whatever it is you ask for, that's what you'll get. Again, it's wired into the standard lifecycle. Uses whichever toolchain. Same sort of options for tweaking, customizing. So let's take a look at that. Windows. So this is our Hello World application. It's been split into a greeting library and our Hello World front end. So what we want to do is we want to compile this stuff up into a library, compile this stuff, and link it all together into an executable. So the build script for this guy has a little bit more stuff in it, mostly related to defining that test executable. So we apply the cpplib plugin to get our by convention library. Then we tweak it as we saw before. We just want to define this DLL export reprocessor macro. So this is about building the library. And then this stuff down here is about building the test executable. So I've defined some test source. So I test CPP source set. And by convention, the source for that guy is in source test CPP, and then source test headers. And we're saying this source has a dependency on the main library. So wiring those two things together. And what that means is that when you compile that source, I need the headers from that library when I'm compiling, and I need the binary, either the shared library or the static library at link time. So whatever I'm linking this guy into, I also need its dependencies. And then I'm taking that source and I'm defining a test executable, and I'm wiring that source in as input to that test executable. So we build a library, we've got some source that needs that library, we take that source and use it as input to build an executable. From that, Gradle infers the right things to do. So, this time I'm going to build my test executable. So, it's kind of done the compilation in an unusual order or an unexpected order, but it's still correct. So the first thing it's done is it's prepared the test headers. Again, that's for setting up headers that are coming from a repository. Because this is all, in this example, the headers for the library are local. It doesn't need to set them up. They're all ready to go, so it doesn't need to do anything there. Then it compiles the test executable, dragging in those headers. Then it compiles the shared library. So it takes the source files from source main CPP and compiles them. And it compiles them so that they can be included or linked into a shared library. So it it compiles them as a program independent, a position independent code, links that into a shared library, and finally links the executable. So let's have a look at what it did there. So it's produced our lib hello world shared library and our test executable and all the intermediate stuff it needed. So let's try running our executable now. So that didn't work because it couldn't find our shared library. It's in a different location to where it's been, where the link is expecting to find it. So we need to, so you can take care of that by, you can install that up in a user local lib, or you can run it with our library path set appropriately. Now it works. So this starts to get painful once you've got 30 shared libraries.
I know it's only an example of tests, but you're not reserving that for convention for like CPP unit type tests or things in the future, maybe? I know it's just a name source set.
Yeah, good. I should have probably called it Hello World or UI, but that's a good question. And yes is the answer. We do want to. Well, and I'll talk about that a little bit later, perhaps. We do want to get some by convention unit testing support in there, and yeah, that's going to be probably the source set that we'll use for unit tests. So so this gets painful once you've got 30 shared libraries coming in from repositories and different projects and install on the system. So Gradle takes care of this to some degree. This is a bit of a work in progress at the moment, but for every executable, you can not only build the executable, you can also install it. And so that sets up a little development image or installation of that executable along with all its dependencies that it needs. And it does that locally in the build directory rather than installing all that stuff up in your lib directories just to avoid pollution. So we can install this now. So let's have a look at what that built. So that set up a little test installation with the things it needs and a wrapper script to take care of setting all the appropriate paths. So now I can run my test executable and it's all happy. It's found that shared library. So yeah, this is a bit of a work in progress because you can't actually debug this. Because it's using a script. So what we'll probably do is sort of turn this into two separate things. One, a way to say, set me up an image I can use to run locally and debug at development time. So get the debug files in there, get the source files in there, set up all the right stuff so I can debug it. And separately, some way to set up an install image, so actual production install that I can take somewhere and unzip. And that can then, what's interesting about that is that we can do all that stuff from what you've told us here. We don't need to know anything more. We've got a high-level description of the executable and what it depends on, so we can infer what you need at runtime, and we can set that up in the installation. We can infer what you need at debug time and set that up as well. So high-level description, Gradle can do some interesting things. We might add a run task, for example, that can run that executable. We might sync that up with the applicant.
In Linux, it is possible, for example, to set an R path for the executable in order to this dependency.
Yeah.
And manually maybe put a library there and set to the executable R path just for the library.
Yeah.
It is possible to do this, or you have to insert the command plug manually?
Well, that's probably how we'll do the dev image. So when you do Gradle dev install, or whatever we call it, it'll probably bake an R path into that executable, and it'll all just be right. But it was still sort of figuring out how we want to do that. But yeah, something like that, definitely. And you could do that yourself. I mean, you could, set some compiler settings here and say, I want my R path pointing at the directory, the output directory of that guy, and then it'll work. But then you can't take that binary then install it somewhere else, because it's pointing at where you built your stuff on your machine. So the idea is that the production binaries, well, we want to distinguish between production binaries that don't have those absolute locations baked in them, unless that's how you install it, and those things you use at development time, where it's okay to bake those things in, those absolute paths and so on, for convenience, for developing, for debugging and so on.
One question. So this install directory, if this project has its dependencies, so all the dependent header files and SO files or whatever will be pulled from repository and installed into that install directory.
Yes.
So I specify dependency section in my Gradle file with some coordinates of a project, and Gradle will find those libraries header files, download from repository, put them into the install directory.
That's exactly right. Yeah, that's the plan.
Okay.
Yes. And we're close to that, but it doesn't quite work because that is the plan. Yes. Okay. So we're not quite there yet.
But if you have multi-project built, how that would work?
Same sort of way. You would just declare same way as the JVM stuff. So you'd declare a project dependency, and that would drag in the right header files.
Via repository or directly?
Directly. So same as with the Java project. So if you declare a project dependency in the Java with the Java plugin, it points directly at the jar locally.
But for each project you keep everything generated locally and no external dependencies locally. So if you share dependencies between 5 of your projects in your workspace, then you will have a lot of duplication.
No, because it'll probably, well, it depends. There's two things. There's where do we point at it when we compile and link? And we'll probably we do point directly into the Gradle artifact cache. So it's all in one location. And then if you make an install image, I mean, the whole idea of the install image is it's a self-contained, runnable image of your executable. So it by definition copies that stuff into that image. So it depends. If you're working in your IDE, you probably don't care about all this stuff. We're going to configure the IDE, just point directly into the Gradle cache. So so that's the plan.
So how do you propose bootstrap? Because most people don't have their C++ headers in repositories. How do you get stuff in
that's a good question.
Start actually working on this?
Yeah, that's a good question. We don't have good answers to that yet. There is that bootstrap problem. One option, so there's a couple of things we're thinking of. Well, I mean, the obvious one is that you manually do that. You just upload that stuff and get started. Another that we're thinking of is is a bit more flexibility in the repository definitions, so that you can sort of deal, because these things, you do have those dependencies, that they are somewhere. If you've got a build right now, they're there somewhere. So to make the repository definitions a bit more flexible, so they can point out where they are right now, but you can still declare them as dependencies, and then over time you can migrate them into a repository. Is another approach we might use there. So just you describe the reality of what you're doing right now, and then you can migrate to a repository manager later.
Is CPP a base plugin?
Sorry?
Is CPP a base plugin?
Oh yeah, sorry. So I missed that one. Yeah. So that's to so that's a general purpose plugin that doesn't define any libraries or executables. It just adds the DSL to let you do that. And I've applied that so that we can do this stuff. So I've just applied that, and then I've defined my own executable here, source.
Is CPP lib dependent on CPP?
It is, yeah.
So if I just said CPP, would it load, or sorry, if I said CPP lib, would it load CPP?
Yes, it would, yeah.
Okay.
So I could have left that out. I kind of put that in there to make that a bit
Well, that's
clearer.
fine. I just, for,
yeah.
yeah.
So you could do that, yeah, absolutely. So it's a base plugin. It adds the capability to build things, but it doesn't add any convention. It doesn't say there is a main executable or there is a main library. That's what the CPP lib and CPP exe plugins do. They say, oh, cool, we apply the CPP plugin, so we've got the capability, and then we say something about the world. There is a main library, there is a main source set, and that's input to the main library.
Mm.
So what about when people want to start developing libraries with variants? One compiled against Boost, one compiled against CPP11.
Yeah.
The same sort of stuff that Android has in the, I can't even call it JavaScript.
Yeah, and we'll get to that. It's definitely a problem we want to solve. Is that's the reality of almost every C++ project, is that you're building multiple variants of the same thing. So we'll look at that in a second.
Will we also look at how we're going to store those in a repository?
We'll talk about how that doesn't. We haven't gotten to that point yet.
Okay.
So okay, so libraries, all very exciting. So we touched on this a little bit. I just want to talk about the model that's underlying all this stuff. So we have the concept, well, the model is that a C++ project is made up of libraries and executables. And these are the high-level descriptions of the software. This says what this thing is. This is a library. This is an executable. Doesn't say anything about how it's built. And then from an executable or a library, you can produce one or more different binaries. And the binary is that component bound to a particular environment. So you've got some examples here. So I might have my Linux 64-bit binary executable and my Windows 64-bit binary. I may have a shared library and a static library binary. So lots of different variations there, or potentially lots of variations there. So the idea, so you've got this high-level thing that can produce lots of specific things, binaries for individual environments. So what you can do is you can wire these things together to make a graph. So C++ source and headers are arranged into source sets. We've already seen that in some of the demos. Source sets are then used as inputs to libraries and executables. And then libraries can be used as inputs to other components. So we see this here. We've got our utility library. We've got a bunch of user source. We can from that we build our Windows shared library, our Linux shared library. And binaries may have variant-specific inputs as well. So maybe our Windows executable has some Windows-specific source, as well as some shared source. When we're building our Windows executable, we need our Windows shared library as input. When we're building our Linux executable, we need our Linux shared library as input. So quite flexible. The by convention plugins take a pretty specific view. You're just building one variant, and you're building it for whatever it is the current platform is. But the underlying model is more flexible than that, so that we can build a whole bunch of different things for the same library or executable. And now this graph can, of course, continue in both directions. These things might come from different projects. They might come from a repository. They might already be installed. Maybe there's an executable that generates this source. So we have a graph of things there, graph of binaries that we're building. So I'll have a quick look at this. We've sort of seen this already with our library example. Here we're wiring things together. We're wiring our library into our source, taking that source and building an executable. So we can change this dependency here to instead refer to the static variant of that library. And this time it's built our static library, it's compiled that source.
So you get those jobs, or those tasks basically for free in there.
That's right. So we use that definition of this is a library. We know that we know that we can potentially be asked for the shared version of it or the static version of it, and then we set up the appropriate tasks to do that.
So what you were showing on that other slide where you had the workflow going from left to right would have probably amounted to a multi-project build?
Well, it depends, but yeah, it's probably,
first and then
that's probably how you'd structure that kind of thing. Yeah. So then you can just use the convention stuff, for example, and they probably are separate things, but it depends. It depends what the relationship between those two things are. So again, you see the incremental builds kicked in here. So it hasn't recompiled our test executable because the header hasn't changed. It's still using the same header. The only change that's happened is that the linkage has changed. So it's relinked the executable, but it hasn't recompiled it there. So another interesting thing, if we just look at that installation again now. So the shared library is not there anymore. So Gradle's cleaned up those stale files. It's not required anymore, so it's gone. So that's another important aspect of the incremental build, is cleaning up garbage that you don't need anymore.
That's nice.
So we've already talked about this really. The CPP plugin is just the base plugin underneath everything that adds the DSL and the concepts, but doesn't say anything about the world. Other than there might be libraries and there might be executables and there might be source sets. So the plugins deal with, or help you deal with, writing portable build logic. So you saw in our example build scripts, we didn't say anything about how to invoke GCC. We didn't say anything about how to name the output files. Gradle inferred all that stuff. So it helps you, it deals with the differences between your operating system, so naming conventions, and the tool chain. So how do I invoke GCC to build a shared library? How do I invoke Visual C++ to build a shared a DLL? So we can customize those. Sorry, yeah.
So A lot of times in a financial institution, there's certain controls, and the way people write their specs about controls these days, they can't let the tool chain float. They've got to be able to say,
Yeah.
this is a very specific version of
Absolutely.
GCC. I know what went in, I
Yeah.
know what came out,
Yeah.
and when we switch, it's a control switch.
Yes.
So how are those types of things supported? You have to be a little bit more specific.
Absolutely. So again, that'll be in the. I was going to talk about that in the when we talk about the variants. But so the floating stuff is something that the by convention plugin does. But each binary has up. You can ask it, what tool chain are you going to be using? So you can basically go, if I'm building this binary, assert that the tool chain is GCC 4.4. The other thing we'll probably do is ways for you to say, so conveniences for doing that sort of thing. So to say, this must be built with this particular version of GCC and only that version. So either fail if you're not using it, if you can't find it, or go and find it. You might also say, we need to build a GCC 3 and a GCC 4 version, and Gradle will also take care of that as well. So that's a bit further down the roadmap, that kind of stuff. We do want to solve that problem because it is an important problem to say. And things like at development time, I don't care. So developers can use any toolchain that's supported, that's fine. But if I'm doing a release, I must use Visual C++ and I must use this particular version of it. So to be able to lock it down by lifecycle as well is important.
Are you going to produce a project file that you can import into Visual C++?
Yes.
Visual Studio?
Yes, we do want to do that.
Yeah, that'd be really helpful.
Yeah, absolutely. And we've got everything we need from that description
Yeah,
already.
that's what I was-
So the model's there, it tells everything we need, so we can just generate that solution file from that
That
stuff.
would be wonderful.
Yeah, and so you can define all your settings, and you've got one source of truth about how to build your software. Generate a Visual Studio solution from that, got all the same settings. No wiki about how to set up your project file, your Visual Studio settings. No, I built it on my machine, it worked. Some guy's got some other checkbox checked. It's just, so yeah, definitely. So we've got that high level description, we can do all kinds of good stuff with that.
Yeah.
And making developers' lives easier is definitely part of that.
That would be awesome.
So let's take a quick look at this before we do. So you can do some customization for all platforms. So you can basically say, regardless of where I'm building this, I want these settings, or for a particular platform. So if I'm building with GCC, use these settings. If I'm building with Visual C++, use those settings. It doesn't help with, there's nothing in there to help you write portable code. All this is doing is helping you write portable build logic. So we don't generate a config.h or any of that kind of stuff. It's only dealing with invoking the build tools and building your stuff. Something to help with portable code is probably would make a nice plugin at some point. Maybe a good community contribution perhaps. But we're not planning on doing that that's not on the roadmap at the moment, that kind of stuff. So, I've got my trusty Windows XP install here. So, I've got Visual Studio installed here, so I'm going to use that to build exactly the same sample we were looking at before. One thing incremental build doesn't help you with at the moment is building on two machines that share the same build directory. So I have to clean. So let's build this thing. So I'll run the install task. So it's driving Visual C++ to build our executable. So let's have a look at what it's done.
So it just intuited what toolchain you had available and just used it.
That's right, yes. So it's built, yeah, so it's taking care of invoking the right,
That's nice.
invoking CL in the right way. It's taking care of the naming scheme. So here it knows that they're called .objs instead of .os. It knows that it needs to build a hello world.lib rather than a lib hello world.a. It knows it needs to build a test.exe. And it's installed that thing. So again, the install task helps on Windows as well, because if you just run the executable, it needs to have all the DLLs in the path. So again, the install image takes care of getting those DLLs in the right place. So we can change this to, so let's change our sample back to shared library now. And build that again. So, let's have a look what that's done. Too much stuff there. So again, it's taken care of all the naming schemes. But another thing it's taken care of is the fact that there's two different files involved with the DLL. There's the file I use at link time, and there's the file I use at runtime. So when it invokes the linker, it passes across the .lib. It doesn't need to do that with GCC, it just passes across the DLL. When it installs it, it knows it needs to bring the DLL across. So I've also got Sigwin here, so I'm going to build with GCC. So different tool chain. Gradle knows it needs to recompile and relink stuff.
Nice.
So it's recompiled the libraries, linked them, recompiled the executable and linked them, and reinstalled because the binaries are different. So let's look at that output again. So GCC doesn't produce a .lib file or a .exp file, so we've cleaned them up. They're gone. So again, the incremental build takes care of removing stale files that you don't need. It's really useful. The stale files are just nasty. So incremental build, we've seen most of this. Gradle, don't clean. Bad idea. But you can get away with it in the Java space because the compiler's quite fast. But in the native space, it's a killer. So we've made incremental build extremely accurate.
So if there is time, no, actually, can you give us a little bit more detail, if it is possible, or how do you plan to do the Visual Studio integration? Because, just for giving an example, we are using CMake that generates the project file, so when the developers change some settings in Visual Studio, so of course this setting is going to be lost, so they need to change the CMake list file, and this brings to a regeneration that usually got stuck in Visual Studio, you have to close it or open it. Are you going to solve this kind of issue, or a little bit what you have in mind, if it is possible?
At this stage, what we're planning to do is just generate the solution files from the build. So that's going to mean you need to change something. You're going to change the build, run Gradle to regenerate your solution files, and then reload them. So it's not going to be quite as easy as just click in in Visual Studio. However, it does mean that everyone's using the same settings, which has its benefits as well. So that's the plan at this stage. We'll see how that works out. At some point in the distant future, it might be nice to have a native tooling API that we can then do some deep integration with Visual Studio. Now we have some native support, maybe we'll do that but that's in the distant future. That's not really on the roadmap at the moment. But that would be another way we might solve that. Is to start getting into some of the build some native tooling and integrate with Visual Studio that way. So yeah, so we've pretty much seen all this stuff. The incremental build, it's all about being accurate, so you don't have to redo work that you've already done, but do that in an accurate way so you don't get strange behaviors of things being half up to date, half out of date. So we deal with changes to header files, source files, settings, changes in dependencies. So you saw before when I switched from static to dynamic, it relinked my executable because the inputs had changed. Deals with changes of toolchain. Shouldn't say platform up there. That's still a work in progress, but we saw toolchain changes, no worries. And cleaning up stale files, object files, executables, debug files, and so on. So there's a couple of things missing with that. At the moment it does what we call incremental build, which is if for a given binary, if any source if any source file is changed or any header file is changed, we recompile everything for that binary. So we don't yet deal with changes to individual source files. So we don't need to if a single source file is changed, we don't need to recompile all those source files. We just need to recompile that guy. And similarly with the header files, we track the header files as a whole. So if any header files change, we recompile all the source for that header, for that binary. So we want to be able to track the dependencies between source files and header files. So if we change a header file, we recompile just the source files that are affected by that change.
How are you planning to handle that? Are you going to look inside the files and look at that, or are you going to have to specify that in some sort of meta information, like in the build itself?
No. The Gradle will take care of it. However it is, it does that. So you won't need to say this source file depends on that header file. We want to infer that, and there's two ways we can do that. We can parse the source ourselves, or we can perhaps use GCC to spit that stuff out. We'll play around with those options and see what we come up with. It might do either. It might go, well, I'll use GCC if it's there, or otherwise, well, we'll have a go at parsing or something like that. So we haven't quite figured out the details of how we're going to do that, but it's something like that. But certainly, you won't have to tell Gradle, this source file depends on that header file, and that header file depends on that header file, but only if that macro is defined, and only if I'm using that header file. None of that stuff.
Good.
Are you planning on wrapping in Gradle some of the common compile and link flags?
Yeah.
Things like multi-threading flags, so
Yeah.
you don't have to go in and remember what the code is for a particular compiler.
That's nice.
Yeah, so we've just done preprocessor defines, just to sort of give you the idea of that's the sort of thing we want to do, but include directories, debug, optimize, some things like that. Yeah, pre-compiled headers perhaps. So some of those are going to have to be conventions more so than, as in we're going to say, well, if you ask for a debug binary, we'll give you out of the box what we think are some reasonable defaults. But if you need to tweak them, you can drop down to the actual command line arguments level and override that stuff. So we want to model some of that stuff so that later on we can make use of it. So you can say, I want to build a debug binary or a release binary. We can understand what that means. We can know that if I'm linking a debug binary, I need to get the debug binary of all my dependencies. And if I'm linking with GCC, I should prefer that. But if I'm linking with Visual C++, I must use the debug variants. So we do want to know that stuff so we can infer some useful things further on. So yeah, incremental build. So most C++ projects produce multiple outputs for a given executable application or library. And we want to solve that problem. It's a common problem. So there's lots of different ways that the output can vary. It can vary by operating system, can vary by the version of the operating system. So maybe I have an optional feature that I support that uses an API that's only on Mountain Lion. So I produce a binary for Mountain Lion, and then with that feature enabled, and then a binary for everything. The earlier for Lion and earlier without that feature. So architecture is another one. 64-bit, 32-bit, PowerPC, x86, all those variations of architecture and chipset. Toolchain and version of toolchain as well. So maybe I'm building a library that some of my consumers are using GCC3 and some of them are using GCC4, different APIs. So I've got to produce two different binaries, or two different variants of my binaries. And these are all dimensions, so you're getting multiple dimensions of variation here. So it's a cross product of all these things that you actually need to produce. So environment, maybe you're building something for static linkage or dynamic linkage. Maybe it's a hosted thing, so a regular execute application. Maybe it's a device driver. Maybe it goes in some embedded device. Maybe you're delivering them as object files. So build type, building release binaries, debug binaries, and anything in between. So maybe optimized debuggable binaries. And then there's just everything else. There's stuff every project's going to have or can have their own dimensions that they care about. Optional features, profiling, blah, 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 blah. So our plan is to take what you've seen there with the multiple binaries for a given component and build the concept of variants on top of that. And a convenience for declaring those things. So basically saying, I build for these operating systems, or these are basically saying the things that I care about. So declare which of those things are important to you and which ones aren't so important. So I built for these architectures and these operating systems and these tool chains, or maybe I don't care about tool chain, just figure it, and so we want to be able to infer the stuff that you haven't told us about. If you haven't told us about build types, well, we'll just give you release builds and debug builds, and that's good enough for you. And so given what you've told us about your world, we then want to define all the stuff for you. So define all those binaries, wire them up, add some lifecycle tasks. They can say, build me everything that you can build on this machine, build me everything for this tool chain, build me everything for this operating system, those kind of things. So we don't have this yet, but this is an important problem that we want to solve.
So how deep do you see this going? I mean, compared to, say, something like GNU's autoconf, that is delving down into what OS calls are available on the particular platform that you're running on.
Well, that's probably more in the config.h kind of problem. At this stage, we don't want to get into that problem. We don't.
It's a fuzzy line.
Yeah.
How much goes into a tool like autoconf, and how much goes into your build automation tool, and it's a very fuzzy line.
Yeah.
There's several tools, different kinds of tools like
Yeah.
autoconf on different platforms.
Yeah. Well, I guess there's a few things. We've sort of ruled out dealing with, we don't want to solve the portable code problem at this stage, so we've sort of descoped that. So we're more about portable build logic. So it's about invoking the compilers with the right flags at the right time, and doing the incremental build. So some high-level descriptions of what you've got, some descriptions of the sort of environments you want to target, and then Gradle kind of marries the two up and builds all these things and wires all the tasks together. But you've still got that lower level to drop down to if you need to. So if Gradle's not doing the right thing, if it's not inferring the right flags, you can drop down and say, actually, you got it pretty much right for everything else, but for this particular variant, I want to tweak this. You might say, for this particular variant, I'm using variant-specific source, so I might say for all the binaries that I'm building on Windows, I need to use that source set as well as my shared source set. I might say for all of the binaries I'm building on Windows, I need that library, and when I'm building on Linux, I need that library. They do the same thing, but they're different libraries. You might have optional features based on platform as well, so maybe your set of dependencies varies based on which features you've got. So, so let's infer what we can, and then let you tweak the rest. Tell us tell us how your world's different to what our convention is.
How much work has gone in so far to look at scalability of compiles for large software projects? I know some CAD tools that we have that have, you know, tens of thousands of source files.
So
you know, scalability becomes an issue in a number of different ways when you start thinking about incrementally compiling something that large.
Yeah. Well, I mean, the starting point is the incremental compilation. So, and compiling just the source files that are affected by a change. We don't want to compile 10,000 files.
It's just the analysis to figure out. Can be
the same sort of thing. The analysis can be incremental as well. So we can use that graph to decide what to scan for changes to. There's a few other things we want to do. Parallel compilation. So compile not just. So at the moment we've got parallel execution across for each on at the project level. So if your 10,000 source files are in one project, you know, you're out of luck in that respect. So getting some some parallel compilation in there, so I can whatever source files have changed. Potentially we could even parallelize the analysis as well, so we can do some of the change checking in parallel. But avoiding building stuff is probably where it's at, and we want to be able to do things like, if the CI build has already built this binary and nothing else has changed, then just go and get it from the CI build.
Yeah, large projects like that today, typically they solve the scalability issues through structural separation. Yeah. But, you know, that's an artificial divide in many cases, just for the performance issues.
Yes. So we want, so we're only just starting down that path with the incremental build. But the plan is to solve those sorts of problems. We do want it to scale to big. So lots of executables, lots of libraries, and things with lots of source. So sort of those two dimensions of scale is what we aim for. And also scale with variance, so number of dimensions. And that's kind of where we're starting. So we've got the incremental build, we're looking at the complexity of, I need to build lots of different outputs for the same thing, just help me out, do that for me. You figure it out for me. So that's that, and that's what this is trying to solve. So an interesting problem there is that when I'm wiring up my dependencies, I've got a bunch of candidates to choose from. So if I depend on a library, I'm building a whole bunch of different outputs for that library. Which one do I choose? So that leads us to dependency management. So it has to be variant aware. You can't. Sometimes you can substitute different binaries in. So I can on Linux I can take my debug. I can take a release library binary and link it into a debug executable. I don't get any of the debugging information, but at least it works. On Windows I can't do that. So it has to be. Dependency management has to understand the different variants, what they are, and has to understand the rules about how you can combine those. It has to make a choice about which variant to use. So dependency management. So we've already seen, so a binary takes a bunch of things as input. It takes source sets as input, libraries, and binaries. When it takes For each source set it takes as input, it needs to compile that first in order to link it. For a library, it needs to choose the right variant, and for a binary, it can just link that in. And in turn, those things take dependencies. So each source set has a dependency on 0 or more libraries or binaries. And those things in turn, so you've got that dependency graph, you've got to resolve conflicts, you've got to choose the right variants. At the moment, the dependencies can come from 2 places. They can come from the same project. As we saw in our examples, we had library and executable in the same project. They can come from another project in the same build, so you can do a project dependency. At the moment, there's a couple of things missing. So resolving those dependencies from a binary repository is a work in progress. It basically isn't quite ready yet, but certainly the plan is that you should be able to get your dependencies from a binary repository manager. You should be able to push your dependencies up there as well. That should all just work. I guess another example, there's potentially a lot of places where we might go and look for dependencies. So from your CI server might be an example.
So in Java, there's all this stuff about when you create artifacts, at least with both Maven and Ivy, there's a concept of extra metadata that helps you figure out how you want to use it. For the C++, you guys proposing packaging extra metadata, or you need to infer it based on other things in the name?
Yeah, we probably won't use a naming scheme. We'll see. We may have to choose a bunch of different strategies depending on what it is that you're doing. The plan is that the metadata has to travel with these things. So even within the same project, when you depend on a library, there's 2 things that come with that. There's the set of headers. Well, there's 3 things actually. There's a set of headers to use when you're compiling against that library. There's a set of files you need to use at link time to link against that library. There's the set of files you need at runtime. So there's already, and also to solve the variant problem, that with those binaries needs to travel things like the toolchain, and whether it's debug or release. So there's already metadata traveling with these things. So we want that to travel also into the repository. It has to. It's just too rich. You can't jam that into a name. It's going to be, a terrible looking name with 30 different fields all jammed into one name. So we need that metadata to travel. So
I mean, theoretically, it should be even pluggable how we persist that metadata.
Yeah, and
if
that's
for some reason you want to have this long name, just plug it in, because the main thing is that the metadata is in Gradle, and then you just have to persist it somehow. Whether this is an ID file, or whether this is our own format, or whether this is the naming scheme. We will provide some good out-of-the-box solutions, but at the end of the day, it should be pluggable, just however you want to persist it.
That's exactly right. Because for some projects, you don't have any variants. So you can use the name because the name is there's nothing to put in the name. So or if you've just got one dimension, if you're just building for different operating systems, it's quite reasonable to put it in the artifact name. So yeah, we want a couple of different strategies for how it is you publish that stuff. How we take our model and map it to the Maven model. How we take our model and map it to the Ivy model. And you should be able to tweak that. So there'll be some degree of flexibility in that mapping to let you say, actually, I want that type of scheme, I want that kind of scheme. Don't do it, I'll do it. I know exactly how I want to call these things. I know exactly how I want to refer to these things. But we'll still have the metadata travel through with those binaries. That's an important thing.
So this will all be fully baked by 1.7, I assume.
Yeah, next week, that's right. So, it does say coming soon, that's probably a little bit ambitious. So here are some of the things that we need to solve in dependency management. We've sort of already talked about most of these things. Dependencies that come from different places. Built by another tool, checked into source, already installed. You need to build them from source. So not just project dependencies and external dependencies.
a lot of platforms have very, very different conventions on that kind of thing. Is that something also looking at making pluggable?
Yes. So again, the idea would be that we should. How many of these we sort of support out of the box is an open question. Probably not a huge number. Certainly not many to start with. But we do want this concept that you can take these things from multiple places, use them as inputs to your build, and then push your stuff out to those same places. I think that's where we want to get to. So the idea is that you've got these you've kind of got the general purpose Artifactory Nexus kind of, not Nexus, but Artifactory repository managers that'll accept pretty much anything. And then you've got these platform-specific repositories and packaging formats. So we should be able to, given the information you've already given us in the model, transform our binaries into those packaging. So we should be able to produce RPMs from what you've told us. We should be able to produce NuGet bundles based on what you've told us. We should be able to push those up into the appropriate repositories. And same with resolving them. We should be able to resolve those things. We should be able to resolve NuGet bundles. Use those things. We should be able to resolve RPMs. We still have to figure out how we translate between those worlds. So there is a mapping exercise there. But it's the same with Ivy and Maven. We've got those formats don't use the Gradle model. They use their own model. So we're mapping back and forth between those things. So same sort of thing. There'll be some sort of flexible mapping you can influence that. Translate everything into the Gradle model, resolve it all, build it all, package it, translate it again, and push it back up. So different sources of inputs, publishing and resolving with a repository. To start with, it'll be an Ivy repository probably, and maybe Maven repositories, and then further down the track we want to get into those more platform-specific repositories. So dependency resolution has to be variant-aware. So in the Java space or the JVM space, we kind of pretend that this problem doesn't exist. We just kind of go, everything's got one jar, we'll grab that jar, it'll work, it'll be great. But if you're building a Groovy library and you've compiled with 1.8, 2.0, you can't do that if you've got a Scala library, 2.8 and 2.10, you can't do that either. So it's not just a native problem. We want to solve this in a general way. It's reusable in other domains. So JavaScript, for example, if I'm building my development image, I want the non-minified JavaScript. If I'm building my production web app, then minify that stuff and get the minified versions of all my dependencies. So this concept is everywhere. So we want to do this in a way so that dependency management doesn't know about C++, the C++ domain. It doesn't know about GCC, and it doesn't know about Visual C++. But those plugins can inject that stuff into the dependency resolution model and influence that, so that other domain-specific plugins can do the same. The JVM stuff can do that. The Groovy stuff can do that. The JavaScript stuff can do that. My custom packaging model for my embedded container can do that. So yeah, that's a problem we need to solve. The native stuff forces that issue. It forces us to solve that problem. We just can't do dependency management without solving that problem.
A lot of the repositories are starting to try to deal with the licensing issue in terms of keeping track of the metadata for licensing, and it's sort of a strange variation on the variance scenario. You know, certain libraries of certain license types are compatible with each other or incompatible. Have you put any thought into, thinking about in your dependency management, including ways of including business logic around licensing coming from these repositories?
Not licensing in particular. That's a good problem. But that concept, exactly that. I have constraints about what. So, I mean, dependency resolution is all about taking a set of candidates for a dependency and choosing the right one, or choosing the best one. And when there's multiple, we need some rules to distinguish between those. And at the moment, we've gotten away with, and this is, we'll get to that in a second. We've gotten away with that in the JVM world because you can kind of just go, it's an 85% solution to say, I can choose what you've asked for, or I can choose anything higher, and it's kind of mostly going to work. And we can get away with that. But with the native stuff, we need rules about choosing those variants, and they have to be domain specific. So because we want to make that extensible, you should be able to, and we do want this to be the case, that you can take your own logic about how to choose from the candidates and apply that as well. So we haven't really talked about doing anything specifically for licensing, but certainly having the concept that you can have rules that choose between candidates. That would let you solve that sort of problem. So another problem we need to solve for dependency management in the native space is the idea of context, or how you're using the thing. So again, in the JVM world, if I'm compiling against a library, I get given the jar. If I'm running against the library, I get given the jar. If I'm testing against the library, I get given the jar. If I'm debugging, same thing. So we haven't needed to care about the fact that these are different ways of using the thing, and you can have different files involved. So in the native space, for example, when I'm compiling against a library, I need the headers. You can't give me the DLL, it doesn't make any sense. Only the headers make sense when I'm using the library in that way. If I'm linking against it, I need the .lib if I'm on Windows, and the .so or .a if I'm on Unix. So you can't give me the headers. Don't give me the headers. Runtime. Well, if you're using a static library, there is no runtime file. It's baked in at link time. But if I'm using a shared library, I need the .so or the .dll. And debug, there's extra files involved at debug time. So we need this idea that the same dependency can resolve to different sets of files at different points in the life cycle of the build of what but that's based on how you're using the thing. And again, we don't want to bake that concept deep into the dependency management. We don't want it to know about headers and link files and debug files. We want the domain-specific plugins to be able to describe that to dependency resolution. And again, that has general usefulness across the other domains. So in the JVM domain, we can use that to solve, and we do plan to use this to solve the idea that things have APIs, and at compile time, don't give me all the runtime dependencies. I don't want them. I just want my compile time dependencies. So at the moment, Gradle gives you all your runtime dependencies at compile time. It doesn't give you just the API of the thing you're compiling against. So we want to use that to improve our other domains as well. And then the final, not the final, but another important problem we need to solve is this idea of must-use dependencies. And what that means is that at compile time, if I've compiled against the headers from this version of this library, then don't at link time substitute in another version of that library. Give me the same version. It doesn't make any sense. It's not going to work in general to give me a different version. In the JVM space, you can vary things all over the place, and we do. So this is baking into dependency resolution and conflict resolution the idea that these things travel together. So you use them at different times and you resolve them at different points in time, but they have to travel together. You have to use the same binary and headers together in general. Unless you tell us otherwise, you may say, okay, cool, I version these headers and it's all backwards compatible, so please just choose the latest version. You can let them float. But you also need to be able to say, well, don't let them float because I don't version those headers. The API changes. So and again, that's another useful thing for other domains. The idea that I have an API module and implementation module. Those things are tightly bound together. They need to travel together. So if I'm using that version, I must use that at compile time. I must use that version at runtime. So really, three really powerful concepts in dependency management that we have to do to solve the native problem, but that are just really useful for everyone else as well. The other domains, the custom stuff. So that'll be fun, solving those. So one last thing I wanted to talk about is standardization. I think this is one area where the current set of native build tools just don't help you at all. So this is I think an important thing that Gradle offers already over other native build tools. The idea that across an organization you've got certain standards that must be enforced. So for example, I've got a build with exactly this version of GCC, or conventions that I should use by default. So my source, for all my C++ projects, my source is in the source directory, and for all my C++ projects, the headers are in headers directory. And for every team, I want that to be the case. They're allowed to vary it if they want, so they can tweak it, but I want that to be an exception. So I want to package that. So I want to standardize that stuff. I want a standard lifecycle that I can use for all my projects, for all my teams. So Gradle's already got all this stuff. We've solved that problem to some degree, to a greater degree in the JVM space as well. So you can do things like configuration injection in multi-project build. So you can, in the root project, you can inject configuration into all the sub-projects. So if you've got a large multi-project build, 1,000 projects, you can say, well, for the whole 1,000 projects, this is the standard, this is the convention. You can take those conventions, pop them in a plugin or plugins, publish them to a repository, share them across all the builds in your organization. You can do that in a change-controlled way, so you can version those things. You can test them before you publish them and before you push them out to the team. Publish them, push them out to every team. It works in really nicely with some of the IDE integration, because now you define your standards in a plugin, you publish that gets shared by all the builds, the developers run Gradle, Visual Studio. Those conventions are all in everyone's IDE, so you can push those things out to all the developers. So really powerful stuff. And it's something I don't think you see in other build tools in this domain. So when you're sharing the same lifecycle with JVM and native projects, if you've got this sort of polyglot stack, which is the reality of many enterprises, you've got a shared lifecycle. You can say Gradle assemble, Gradle clean, Gradle test. Those abstract concepts those lifecycle steps are there regardless of what type of project you've got, what it is you're building. You've also got the wrapper for pushing out Gradle distributions and your own plugins as well. So, good stuff there. Briefly mention, so we've pretty much talked about this. For Eclipse CDT, you can do Gradle Eclipse and you get the CDT config files generated for you. You load them up in Eclipse, it's all there. And we want the same thing for Visual Studio as well. So, hopefully we've kind of answered this along the way. Why Gradle for C++? So we've seen this is the stuff we've seen so far. You've got a high-level description of the software, that you can talk about your software in a level that sort of is flexible, but still high enough that you don't have to tell us the whole world. Portable build logic, dealing with platforms, dealing with tool chains. It's a rich model, so it's flexible, so you can wire those binaries together however you like. You can go with the conventions, you can change the conventions, you can do your own thing. You can drop right down to the compiler level and say these flags for the compiler, these flags for the linker, for this particular binary, these dependencies for that particular binary, that source. Accurate incremental build, so you don't have to rebuild everything. Dependency management helps you with standardization across the organization, across your teams. Helps you build, helps you deal with the differences between building JVM stuff and native stuff, and some IDE integration. So that's all there already. That's all in 1.7. Of course, there's lots of things we want to, as we've talked about, we want to add. So very briefly, we've talked about most of these things, and I'm sort of running out of time. So something. Yeah, we've talked about the only thing there we touched very briefly on testing. So yeah, we want to get the standard the concept of testing into these native projects to say there are things such as tests. Exactly which tool you're going to use, that's your choice, and there'll be different plugins to integrate with different testing tools there. But that concept we want to bake in. Different languages. So Objective-C. Probably into the .NET space as well. We talked about this in passing. So we have this high-level concept of a native application. We also, in the Java space, have the application plugin, which has a high-level concept of a Java application. But they share a lot of stuff. So you want to be able to build a zip distribution and publish that. You want to be able to run that. You want to be able to install that. So we want to sync those up so they share the same model underneath. You can build distributions from them, build installers, native packages. So you should be able to take your Java library and build an RPM for it. You should be able to take your native library and build an RPM for it. You should be able to take your Java application and build an OS X application bundle for it. You should be able to take your native application and do the same. So the difference is only in how they're compiled and the things that get bundled. But once you've got that difference, that's it. Everything else is the same. So they have dependencies, they get packaged, they get installed, blah, 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 all the same. So we want to sync that up a bit more. The other interesting thing we haven't really touched on before is this guy. So using the slaves in your CI infrastructure to do builds. So there's lots of good reasons why you might want to do that. One is so you can do a single build invocation that builds everything for your project. So build it for all platforms, all architectures, all tool chains. Just go and find a CI machine, go and find a CI slave that meets those criteria, spin it up there, spin it up there, spin it up there, gather all the results up, package them up, and publish them. And of course, distributing the work as well, so speeding up your build. So taking the compilations and shipping them around to a bunch of different places. Shipping the variants around and building them in lots of different places at the same time. Really cool stuff. Probably more in the distant future, that one, than the 1.7 time frame. So any more questions?
I mean, the C++ stuff is really great. The work that you guys did that ended up being with the IDE and but Android, there's a specific company driving some of that. The C++ is it just out of the goodness of your heart, or is there's a lot of pressure from potential customers?
This work is some sponsored work, so the company's sponsoring the work. But I think there's a lot of interest in this stuff. So there's been lots of interest in having Gradle. So teams that are using Gradle for their Java stuff going, this is cool. We've got all this. Sometimes legacy, sometimes not. C++ stuff we need to build as well. It's a completely different world, different build system. We just want it as one thing. We want that standardization. We want all the other goodness that Gradle gives us. So yeah, all of the above, basically. The goodness of our hearts, lots of pressure, and it's also being sponsored.
Are you looking at mostly driving command line tools, or are you looking at some of the things that are, compilation as a service? I mean, right now Gradle, because of its Java history, has an embedded Java compiler where you've got deep integration.
Yeah.
That kind of thing is possible in C#, it's possible in GCC, it's possible in the Microsoft compiler, where you get deeper integration, and instead of calling some command line tool, you, for example, use some of the incremental compilation features that are, for example, coming in Java 8.
Yes, yes. I mean, I think that stuff will be inevitable as we get further along, and we need to push more and more performance out of this stuff. Or better feedback would be the other thing, so better reporting. I was thinking about the test integration actually as a place where we might start with that kind of thing, when we need to, we rather than just forking an executable that has the tests and the test framework and the production code linked together, linking some of our code as well so we can get the logging and the reporting and the feedback in the IDE and stuff like that. But same thing for compilation, we can definitely do that kind of stuff, absolutely.
The reason I asked is you'd think it might change some of the abstractions you might want to use if you're thinking about doing it that way. Or deeper integration.
Possibly, yeah. Possibly. Maybe we should look sooner. Yeah, possibly. The idea is that you shouldn't, for the most part, care about how. You should tell Gradle what you want to have happen, and have Gradle can then choose the best way of doing that, or at least a good way of doing that, given the tool chains that you're using. And then if it decides to do something embedded or not, that should be, mostly it's business. But we want some way to influence that, but that should be the idea is that you deal with these things at a higher level than how do I invoke my compiler. You just need to say, Gradle, you need to compile this, and it needs to have, you know, these preprocessor defines and these dependencies, but just figure it out for me. Just do it in the best, quickest way you can possibly do it. So that would be our strategy. Maybe that won't work out. Maybe as we get further down, we'll need to rethink that. But that's our plan at the moment with that. Try and keep that stuff a little bit, certainly a lower level concern. So you shouldn't need to. You can still reason about you can define your software and reason about the dependencies between it and what it is that you produce without caring too much about how the tools are being invoked.
You run into the same kind of abstraction of who's the driver in the IDEs today in the Java. So looking at the IntelliJ and Eclipse and the work that happened in Android to make Gradle the driver of the build as opposed to the IDE. It's the same kind of thing.
Right. So as in you'd be thinking about sort of pluggable options for this sort of stuff. So you can say, Gradle, actually you get it completely wrong, so I'm going to do it all. Is that the sort of thing you?
Well, a lot of the roadmaps of the compiler companies are trying to
push stuff up.
Push stuff up
yes,
into
absolutely.
the compiler or into their tool chain or into their build environment.
Yes, right.
And
so there's some overlap there.
There's some overlap, and that's why it's interesting to me.
Yeah, yeah. I guess if the compiler's going to do a better job of incremental compilation than we're going to do, and we're using a compiler that can do that, we'll probably delegate to the compiler to do that, and maybe fall back to incremental build instead of incremental compilation if the compiler doesn't support that. So we might do that kind of thing. You're still getting the right results. It's just it's not going to be as efficient in that case where it has to fall back. So, but still, you've still got the same interface to the tool. You're still saying, Gradle, build this thing, build it this way, make sure it gets compiled, make sure it gets linked. Just do it. Do it in a good way. Make it fast. So I think that could still work.
Are there any plans to include in Gradle a common model for distributing the build on several hosts?
Yes, we do, and we want to start with the using your Jenkins slaves to do that. So we've already started down this path to some degree. There's already some. We're talking with the Jenkins guys, Koshka and some others. Stefan, yeah. About so a couple of things we want to do there. So distributed testing. So at the moment, the test task, in the JVM space. The test task can distribute the tests across multiple processes locally. We want to be able to spin up those workers on CI slave machines as well. So you can basically say, you know, use my Jenkins build farm, spin up as many test workers as you possibly can, maybe some locally, maybe some remotely, and just hand out work to them, collect the results. So for testing, and then also for building as well, same sort of thing. You want to say, okay, cool, I've got 10,000 projects, just distribute them around whichever machines you can find, collect all the results at the end. And same with that's for scale, and with the native stuff we want to do that, but also for letting you build multiple, as many variants as possible in one build invocation to say, okay, cool, build my Windows stuff and my Linux stuff and my whatever all in one go, and bring the results back, and or take the results and push them up to a repository. So yeah, yes we do, basically, yeah. Questions? All right, thank you everyone.